Hopefully with this video you'll understand some basics on how to analyze experimental uncertainty. So first of all, let's talk about the devices that you'll usually use in high school physics. You have analog and digital devices. The difference is that on analog devices you directly read a physical scale, whereas on digital devices it's a screen that spits out a number. Newton meter first on analog devices, it's to measure forces and it uses Hooke's law. Which states that force is proportional to the extension of a spring, and therefore if we calibrate the Newton meter properly, well, we have a direct correspondence between how much the spring extended and how much tension force was applied to the Newton meter. Then we have measuring tape to measure distances. The caliper to measure also distance, well, rather size of objects with a higher precision than a measuring tape. The thermometer to measure temperature, and which uses the fact that alcohol expands in proportion with the temperature at which it exposed, and the alcohol is usually dyed in red so that we can see it expand. Then on the digital side, we have the stopwatch to measure time, the scale to measure mass, multimeter to measure current intensity or voltage. So with this set of devices, these are the most basic devices, in fact, we use in high school physics. And there's a fundamental difference in the raw uncertainty of the measurements that you do with analog and digital devices. And let's explain this with a quick example. So with the measuring tape, for example, you're measuring the size of something, and usually your scale is in millimeters. So maybe here you have, let's say, 1 millimeter, here you have 2 millimeters, here you have 3 millimeters. And when you read the size of something that's around 2 millimeters, well, usually you'll conclude that it's 2 millimeters long if the size of that thing is between these two red lines, right? So it means that in fact you read 2 millimeters plus or minus 0.5 millimeters. You're at most wrong by plus 0.5 millimeters or minus 0.5 millimeters. In fact, when you're reading 2 millimeters here, you're reading something between 1.5 and 2.5 millimeters. For digital devices, the situation really is that simple. Let's take the stopwatch as an example. We're reading 12.60 seconds. So for any digital device, we just take this last digit that the screen displays, and we just say that we're unsure about this last digit. So here we have a reading of 12.60 plus or minus 0.01 seconds to express that we're unsure about this zero here. We're somewhere between 59 and 61/100th of a second. Let's now talk about systematic error, which is a measurement of accuracy, and random error, which is a measurement of precision. And this is something students usually have a hard time with. They usually make a confusion between the two, usually thinking they're pretty much the same thing, but they're very different. In experimental physics, accuracy is one thing, precision is another thing. So basically, you're not being very precise when your measurements are all over the place. Like in these two examples, for example, where your precision of your device could be something like plus or minus 1 centimeter, whereas there's another device that could give you a better precision here of plus or minus 1 millimeter. So precision and random error is whenever you have this plus or minus effect, which is rather large or rather big. Systematic error, on the other hand, is rather large when you have a bias in your measurements. They're all off by a certain value. Here, like they're all off, let's say, by 1 centimeter, both here and here. Whereas on the top examples here, you're rather accurate because your values are all centered around the center of the target, so you don't have any bias in the way you're measuring things. Now, these are common causes of systematic error. First, we have the problem of calibration of devices. If your device is poorly calibrated on 0 whenever it's not measuring anything, well, then you will always have that amount of error for every measurement that you do. Here on this scale that's measuring the mass of objects, all your masses will be inaccurate by that amount. Then you have parallax error, which is the way you observe the measurement, for example, on a cylinder that's measuring volume. Here, if you're measuring the volume in milliliters and you're constantly looking above the liquid level and not just at the level of the liquid, then you'll always be off here by 1 milliliter. And finally, let's say that you're doing an experiment with a mass spring system and that you choose different masses as your independent variable. So for example, 100 grams, 200 grams, 300 grams, etc. Well, if you neglected the fact that your spring also has some mass, well, it means that in fact you're not really using the correct mass and all your mass measurements are off, let's say by 10 grams if that's the mass of the spring. So here there would be 110, 210, 310, etc. All my measurements were off by 10 grams. Let's now look at sources of random error. So the most obvious one is due to the precision of the devices you're using. If you're using a caliper, for example, to measure the size of an object, its precision is 0.025 millimeters, and that's rather impressive. It's a 40th of a millimeter. Then there's reaction time, because even though your stopwatch may have a precision of 0.01 seconds, well, you're not a Jedi Master, so you're not precise to that level when you're measuring some duration. Let's say that you measure a duration of 0.55 seconds. How do you determine your reaction time on this? Well, you just measure the thing again. Okay, you repeat some measurements, maybe you obtain 0.60, then 0.52, then 0.57, so you made 4 measurements to see how well you're doing in general. And the way to calculate your reaction time, well, you take the minimum and the maximum value and find the spread between the two, so 0.60 minus 0.52 in this case, and you divide this by 2, which gives you your reaction time here of 0.08 divided by 2, so plus or minus 0.04 seconds. So this is a measurement of the random error due to your reaction time when measuring this duration. When you'll be doing experiments in circuits, you'll usually be measuring voltage and intensity across a certain component. And let's say that at some point you measure an intensity of 0.12 amperes, and that the minimum voltage for which you find this is 4.20. And then you realize that by increasing the voltage, you don't increase the intensity yet. You go to 4.21, you still get 0.12. 4.22, 4.23, 4.24, you still didn't change anything to the intensity. And it's only when you get to 4.25, let's say, that this goes up to 0.13. So from 4.20 to 4.24, you stayed on this 0.12 value. This means that when the intensity is 0.12, the voltage you measure is 4.22 plus or minus 0.02 volts. So your precision here on the voltage is plus or minus 0.02. The last example of things that generate a random error is you again not being Superman and not clicking perfectly where you need to click when doing a frame-by-frame analysis on Logger Pro. So you'll be clicking on where your projectile is frame by frame, and of course you can't be perfectly precise in this operation. So maybe it will have here an impact of being, for example, plus or minus 5 centimeters precise, considering the actual position of this projectile in the real world where it was filmed. We're now going to take a look at how uncertainty propagates when you make operations on numbers that have an uncertainty. For example, here I have a rectangle of length 1 meter and width 50 centimeters. And my 1 meter length is plus or minus 5 centimeters precise. And notice here the coherence in the way I wrote the measurement and its uncertainty. I'm unsure about the centimeter value here, and here I have indeed plus or minus 5 centimeter. So it would be incoherent if I wrote 1.0 or 1.000, because it's really here the centimeter value on which I'm unsure of. So now the question is, for example, if I was adding up the length and the width, what would be the result of this operation? Well, it would be equal to 1.50, that's the easy part, plus or minus what? Well, the uncertainties add up, so it's plus or minus 7 centimeters. Okay, another question. If I'm subtracting the length and the width, what happens? Well, I obtain 0.50, that's again the easy part, and here again the uncertainties add up. Okay, you don't subtract uncertainties. When you're making addition or subtraction, the uncertainty worsens exactly by the amount of uncertainty that you have. So we're adding the 5, plus or minus 5 and plus or minus 2 centimeter uncertainty here again. What happens now if I multiply a variable by a number? So let's say that I want to find the perimeter of that rectangle now, and I know that the perimeter is equal to 2L plus 2W. So now how do I find the uncertainty on 2L? Well, intuitively, you'll probably think that it's 0.1 meter, and you're right. You just have to do twice the uncertainty because 2L is just the same thing as L plus L, right? So in the end, the perimeter is equal to what? It's equal to 2 times 1 plus 2 times 0.5, so it's equal to 3.00 meters plus or minus what? Plus or minus 2 times 0.05. So 0.1 plus 2 times 0.02, which is 0.04. So you obtain plus or minus 0.14 meters, and that's the perimeter. So now imagine I'm multiplying or dividing two variables together. The same thing happens in both cases. You add up the relative uncertainties, and I realize I made a little mistake here, uncertainties. So yes, imagine I'm now calculating the area. So the area is the multiplication of L and W. And what do I obtain? I obtain, well, 0.5 meter squared. But now, what is the uncertainty on that value? Well, to find the percentage uncertainty of each of these, I just do for the length 0.05 divided by 1.00, and that's equal to 5%. And the relative uncertainty of this value is 0.02 divided by 0.50, and that's equal to 4%. So here I'm saying that the relative uncertainties add up when I do such an operation. So here I have to add 5 and 4% together, and I obtain an uncertainty of 9% for this multiplication. And I imagine I want the absolute uncertainty that corresponds to that. Well, I have to multiply 9% by 0.50 again, and that's approximately 10%. Let's round it to 10%. So I have 0.50 plus or minus 0.05 meters squared. Now let's say I have a little cube here of side A is equal to, let's say, 10 plus or minus 1 centimeter, okay? And I want to find the volume of that cube and its uncertainty. So the volume is equal to A cube. And here, when you put a variable to a certain power, well, it's like doing A times A times A, right? So it's logical that you multiply the relative uncertainty by that number because you're just doing a multiplication in the end. So the volume is equal to 1,000 centimeter cube plus or minus, well, 10% times 3, so that's 30%, plus or minus 30%. Again, imagine I want the uncertainty now in absolute terms. I have 1,000 plus or minus 30% of 1,000, that's 300. So plus or minus 300 centimeter cube. Let's now apply what we learned to an experiment where the goal is to measure the strength of the gravitational field and to also know how precise we are in this measurement. And we're using here a ball that we're dropping over 2 meters, and there's a certain uncertainty on this measurement of distance. And we measured the time it took to cover that distance. and it has an uncertainty of 400th of a second due to the reaction time of whoever was using the stopwatch. Now to calculate g and also know the uncertainty on g, we can use the uniform acceleration of, equation, which is s is equal to 1/2 of at squared. Here, in fact, the acceleration is simply g because we're in a free fall situation. We drop the thing from rest, so there's no plus ut term to add here because there's no initial velocity. So we just have s is equal to 1/2 of gt squared, and by manipulating this equation to isolate g, we obtain g is equal to 2s over t squared, and when we plug in the values, we find that a value of 10.7 meters per second squared. But now we have a question: what is the uncertainty of that 10.7 figure? So first, let's figure out the uncertainty up there. We have 2s, so we just multiply the absolute uncertainty by 2, and we know that 2s has an absolute uncertainty of plus or minus 0.04 and a relative uncertainty of 0.04 divided by 4, because 2s is equal to 4. So we have a relative uncertainty of 1%. Now, what about t squared? To know the uncertainty on t squared, first I need to know the relative uncertainty of t, which is 0.04 divided by 0.61, and I obtain approximately plus or minus 6.5%. So the relative uncertainty on t squared is twice this uncertainty, so it's 13%. And finally, what I'm doing is that I'm dividing 2s by t squared. And what is the uncertainty on that? Well, I know that with division, I have to add up the relative uncertainty. So here, the relative uncertainty of that number is 14%. And now we have one last operation left. We know that the uncertainty on our measurement of g is 14%, and we want to have it in absolute terms, so we have to do the calculation 14% times 10.7, and we obtain 1.5. So we measure g to be 10.7 plus or minus 1.5 meters per second squared. And the final challenge of the video is to know how to learn how to compute the uncertainty on a gradient. So imagine that you did this experiment of measuring the acceleration of an object sliding down a ramp, and that you measured for different distances the time it took to do this. You processed the time variable and found t squared over 2. Why did you do that? Because s is equal to 1/2 of at squared, so s is equal to at squared over 2, meaning that a should be the gradient of the s versus t squared over 2 graph, right? We have something that looks like y equals ax. So since s is equal to a times t squared over 2, this gradient of 2.6 here should give us the acceleration, 2.6 meters per second squared. That's the acceleration of that object. And now, if we want to compute the uncertainty on this 2.6 figure, well, what we do in the IB, I mean, that's just a method that's suggested by the IB, but it's to look at the first error bar here, the one that's at the very bottom or at the very left, and the last one. And these are the error bars that will serve us to calculate the uncertainty. And what do we do? Well, we first draw the steepest possible line going from this point to this point. So that's this blue line here that has gradient 3.5. And then we draw the shallowest possible line going from this point, to the two most extreme points of the two extreme error bars, and we obtain this minimum gradient of 2.2. So how do we get the uncertainty? Well, we get the spread between these two figures, 3.5 minus 2.2 divided by 2, and we obtain about 0.7. So the final result we found was 2.6 plus or minus 0.7 meters per second squared, and that corresponds to 2.6 meters per second squared. In relative terms, what was our uncertainty? It was something like plus or minus 27%. So not great, but that's what the result is, and that's how you find the uncertainty on a gradient.